So this is going to be a video on chapter 9.5, which is about tangents to circles. So let's go ahead and get started by defining what a tangent is. So a tangent is usually something that you get a teacher to go off on so they don't have to do any work that day. But in math here, a tangent is basically a line, or it could be technically anything, but usually it's a line, that quote-unquote intersects the circle at exactly one point. So this is commonly defined as a line that does not go through the circle, it just touches the circle. So think about this as like the ground and a ball resting on the ground. So that ball is tangent to the ground at that point because it's not going through the ground, it's just touching the ground at that one point and that's it. Now obviously it doesn't have to be in the ground, you can have a tangent like right here. Have that be a tangent if I actually could draw my lines right. It's like that. Just kind of imagine that as one solid line there. That's kind of going through the circle, so let's scrap that. Let's see, if we draw a new circle right here, like a tangent like this. So that'd be a tangent, this would be a tangent, so on and so forth. So a tangent is a line that does not go through the circle, but just kind of touches or rests on the circle. Now there's two theorems that go along with this. First off, if a line is tangent to the circle, then it's going to be perpendicular. I'll just put perp for short. Perpendicular to the radius at the point of tangency. So that means that if I have a circle here, and I draw a line that's just touching the circle like that, that means that the radius of this circle is going to be perpendicular to the line at that point. At that point tangent. Not any point, but just at that point of tangency is the radius going to be perpendicular to it. And the second one, this is one we're going to use a lot more often, is that if two segments from the same exterior point are tangent to the circle, then they are congruent. So basically that means if I have a circle over here, and I have a line here, and a line here, and they come from the same point, and they're both tangent to the circle, that means that they are going to be congruent to each other. Now this one doesn't quite tangent there. Let me see if I can draw my circle a little bit better. So I'll give myself a little bit more room there. But any lines that are tangent to the circle that come from the same point, that originate from the same point, are going to be congruent to each other. So using these two theorems here, we're going to solve some problems. So first, we're going to start with the basic ones, which is just straight applications. Like in the first one there, how do we figure out how big each segment is? Well, we just said that if two lines come from the same point and are tangent to the circle, that means they're going to be congruent to each other. So we're going to do just that. We're going to set 4x plus 7 equal to 7x minus 8. And we're just going to solve that equation through. Again, I'll save the boring draw of doing the algebra. So this would be 3x be plus 15 divided by 3. It's a 3, by the way. And we get 5 is equal to x. And if we plug 5 in, we should get that that's the same thing, right? 4 times 5 is 20, plus 7 is 27. 7 times 5 is 35. Minus 8 should give us 27 as well. This one's a little bit more interesting, or a little bit more difficult, I guess I should say, one of the two. Is that, remember, a radius is going to be perpendicular to the line at the point of tangency. So right here is a right angle because they're perpendicular. And then, lo and behold, we have our right triangle, right? So we have 10 squared plus 24 squared is equal to x squared. Okay? So again, we have a right triangle situation, but probably not one we've seen too often, right? Usually we've done right triangles inside the circle, but now we have right triangles that can pop up outside the circle. If we do the math here, I believe we end up getting 26. I might be slightly wrong on that, but this looks to be like a 5, 12, 13 triangle. So this is 5 times 2, this is 12 times 2, this would be 13 times 2, because 5, 12, 13 is one of the triples. But feel free to check my math and do the Pythagorean theorem for that. Sorry, my throat's a little raspy here, I'm not sure why, so hopefully this is going to come out to be an okay audio. Alright, so this one's a little bit more interesting. It looks almost exactly the same as the last one, right? I mean, heck, it's still a right triangle problem. What's the big deal? Well, if you look here closely, I want to find out what x is. But I only have basically one. I know that this is 14, but that's it. Like, I don't know what this side is here. I don't know what this side is here in total. I know that part of it's 4 and part of it's x, but I don't know what the entire side is here total. So how do I solve for x? Well, first we have to note that we have two radii going on here, right? We have this radius right here, and we have this radius over here. So this is also x because this line and this line are both radii of the circle. And we know that all radii are equal. Again, radius, the plural of radius is radii. That's why I'm saying radii, just in case we didn't know that. So this line right here is going to be congruent to this line out here. So both of these short lines are x. That's all well and good. Still haven't really solved it though. So we need to recognize that this entire length, as I said before, this entire length is 4 plus x, right? Again, just combine the 4 and the x together, you get 4 plus x. So if I want to solve for x, I'm going to set my Pythagorean theorem, but in a very special way. We get 14 squared plus x squared, that's these two sides, is equal to parentheses 4 plus x parentheses squared. You have to make sure you're squaring the entire thing here, because this entire side is 4 plus x. Not just the x, but the entire side length is 4 plus x. Now, when we do this here, 14 squared, if I get my calculator here, I believe is 196, but I want to make sure I double check myself there. So 14 squared is indeed 196. 196 plus x squared. Over here, remember, this is the same as saying 4 plus x times 4 plus x. So this means that you're going to have to FOIL this out here. So you're going to end up with 16 plus 8x plus x squared. Now, luckily enough, when you go to solve this, you subtract x squared from both sides, it cancels out. So your x squared goes away right away, which is good because now you don't deal with the nasty quadratic. So this cancels and this cancels. So now I'm left with 196 is equal to 16 plus 8x. And then I can solve it just like, again, a normal algebra equation. So I get 180 is equal to 8x divided by 8, and I get whatever 180 divided by 8 is. So 180 divided by 8 is equal to 22.5. So 22.5 is equal to x. And then I can figure out the length of each side if I want to individually. So the radius is 22.5, and that means that the entire length right here is 26.5. So again, a little bit more complicated of a problem that still has the same essence of what we've done before, right? We've done triangle problems and Pythagorean problems and side circles before. This one's just a little bit trickier. There's a little bit of a twist on it, but it still goes to the core of setting a Pythagorean theorem correctly and solving it through. Now this one's a little bit trickier, but when you see the trick, it's actually easier. Because remember, what was that second theorem we did, right? If two lines are tangent to the circle from the same point, then they're congruent. Well, here's point N. Here are two lines that are tangent to the circle, and they both come from point N. So if this is x over here, that means this is going to be x over here. And we're just going to go down the list doing this here. So let me see if I can do a different color here, because I have a lot of black already. So this is going to be x over here. And if this is 8 over here, well, the other line that comes from R, that's going to be 8 as well. And if this is 9, that means this here is going to be 9 as well, because they're both coming from the same point. And this is x minus 4, this is also going to be x minus 4. So if I want the perimeter of PNRM, so this basically, if I want the perimeter of this outside quadrilateral, well, I just need to find the size of each piece and then add them all together. Well, I know that this piece right here is 18, right? So this is 18 over here. So if this is 8, that means this has to then be 10, because that way 10 and 8 would make 18. And this is just a chain of events now. So if this is 10, well, that means that this is 10. And if this is 10, well, that means that this is 10 minus 4, which is 6. And if that's 6, well, then this is also 6. So again, once you figure out one piece, it just kind of snowballs into the other pieces there, because everything just kind of click, 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 clicks. And then to get the perimeter, you just add them all up. So we have 18 plus 10 plus 6, which would be 16, plus 6 plus 9, which would give you, plus 6 plus 9, which would give you 15, plus 9 plus 8, which would give you 17. And so you'd add up those pieces together there, just to make sure I don't mess up in my head here. So 18 plus 16 plus 15 plus 17, and you end up with 66. So that would be the perimeter of the shape there, 66 units. So once again, as I told you, the theorem of if two lines come from the same point and are tangent to the circle, then they're congruent. That's a very powerful theorem because it allows us to drag in the outside shapes and connect them to the circle in a way that's beneficial to us. So that second theorem there about being tangent and being congruent, Make sure we don't forget that because that's going to be key to most of the other ones there. Again, the radius one is important. The radius one we use a lot when we're doing stuff like this with the right triangles. So if you see a triangle, you can always check to see if it might be a right triangle using some tricks there. But the other one is pretty darn important as well. Okay? So let's do one word problem here. So we have a satellite 720 kilometers above the Earth and has a radius of 636 kilometers, or 6,000 rather, 360 kilometers is what the Earth's radius is. What's the distance of one of the tangent lines from the satellite to the Earth? So here's the Earth, as best I can draw. It says it has a radius, put the center there, radius of 6,060, or 6,360 rather, 6,360. And the satellite's all the way up here, beep, 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 right? Little satellite there. And it is 720 kilometers above the Earth, 720 kilometers, right? So this is 720, this is 6,360. Again, don't go by scale here because that does not look like it's drawn to scale. What is the distance of one of the tangent lines to the satellite? So here's a satellite. I'm going to draw one of the tangent lines as best I can. So that's one of the tangent lines. I want to know what is that distance. That's my x. What is that distance? Put a little tangent point there. Well, first off, let's go ahead and figure out what this total distance is because I bet we're going to need that. So this total distance here, 720 plus 6,360. So 6,360 plus 720 is going to give me 7,080. 7,080 kilometers. And if I draw this line in here, well, this line down here, this special line down here, well, that's just a radius. That's also going to be 6,360, right? Because all the radii are equal to each other. Again, a very powerful theorem as well. So now I have, once more, a right triangle. And you might be saying, well, where's your right angle? Well, remember, it's right here. If a radius connects to a tangent point, then it's going to be perpendicular to it at the point of tangency, which is right there. So now I have my right triangles before. I have x squared is, or x squared plus 636 squared, or 6,360 squared, I keep saying 636, is equal to 7,080 squared, right? I have my leg, and my hypotenuse. So again, don't forget that all radii in a circle are equal, and you can draw your own if you need to in order to help fill out a shape. So just to run this through here, that's the square root of 780, whoops, try that again, the square root of 780, 780 squared minus 6,360 squared, and we end up getting an x value of 3,110 kilometers. So 3,110, roughly, again rounding. So once more, draw your own radii if you need to help construct what shapes you want to do. Right triangles are very helpful, so don't be afraid to draw in a radius or two to help you use a right triangle to help you figure out missing pieces and construct an answer to the problem. Okay? So that might be our homework, and not sure when this is going to air or when we're going to get to this, but make sure you're willing to check Schoology and make sure that this is actually correct there. But that will be it for this video here. Once again, not too many new stuff here, but very important information. Because like I said, the tangent line stuff is going to be our bridge to connecting other things in the circle as well. And it's basically our gateway to being able to work with outside figures and outside points and connect them to what's happening inside the circle. So hopefully this video helped you out. Have a good day or night or whenever you're watching this.